Hello, everybody. Welcome to today's class seminar. I'm happy to be hosting this seminar today after more than 1 month. Today we have 3 speakers and 2 talks. Our first speaker is Chenhui Shu. He's a PhD candidate in computer science and engineering at the University at Buffalo, advised by Jinjun Xiong. His research spans machine learning, scientific computing, and multimodal AI with a focus on PINNs, geospatial vision language reasoning, and high precision numerical learning. He leads open source projects such as PINN Mamba, GeoR1, and his work has appeared at top ML venues including NeurIPS, ICML, and ICLR. Our second speaker, who is Chenhui advisor, is Dr. Jinjun Xiong. He is an Empire Innovation professor in computer science and engineering at the University at Buffalo, where he directs the Stani UB Institute for AI and Data Science. He also serves as scientific director of the National AI Institute for Exceptional Education and leads AI efforts for the National Center for Early Literacy and Responsible AI. Previously, he was a senior researcher and program director for AI and hybrid cloud system at IBM Thomas J. Watson Research Center. His work spans across stack AI systems from application and algorithms to tools and architectures. And he has earned 9 Best Paper Award, 10 Best Paper nominations, and top honor in major international competition. With that introduction, the floor is yours and you can start your presentation.
Okay. Thank you for your introduction. I will start my presentation today. So, in the realism of the science and engineering, solving partial differential equations is the bedrock of understanding complex physical systems, from fluid dynamics to electromagnetism. Traditionally, this has relied on computationally intensive numerical method like finite element method or computational fluid dynamics. So in recent years, a revolutionary paradigm has emerged called physics-informed neural network. However, despite its promise, PINN harbors a critical and long misunderstood flaw. This report, we will dive deep into the PINN's failure modes and uncovering a door discovery related to modeling, optimization, and numerical precision. So the core idea of PINN is merge two powerful domains, the function approximation capability of deep learning and priori constraints of physics knowledge in the form of PDEs. The goal is to create a universal solver that can learn from both data and the law of physics. This paradigm promises a revolutionize scientific computing. Yeah, so to understand PINN, one must first understand its operation. The PINN workflow is an elegant closed-loop system that transforms neural network training into the physics-constrained optimization problem. So the core workflow of the physics-informed neural network can be broken down into 3 key steps. The first is function approximation. A standard DNN neural network is used as a universal function approximator. It takes spatial temporal coordinates, here x and t, as input and outputs a candidate solution uxt. The network weights and bias are trainable parameters of the solution. And also we include in the PINN automatic differentiation. This is a magical PINN network. Auto differentiation is used to compute the first order differentiation of the candidate solution uxt with respect to its inputs. But not only the first order, you can also compute the second, third order of the differentiation of the UXT. So uh, in the third part, we have a physics-informed laws. These derivatives are substituted back into the original PDE to calculate the residual. So, for example, if the PDE is for example, a very simple PDE, we can uh, try to compute its partial u to partial t plus partial u to partial x. We equal that to so we optimize this residual to 0. Then we can assume this DNN be the approximator of the function. Yeah, so the in the loss function part, basically we have initial condition loss, boundary condition loss, and the governing PDEs loss. In some case, we can also add some data loss into it. After this optimizer, usually we use LBFGS second order because the DNN used in the PIN is not very large. So we can try to this pseudo Newton method. Yeah. Mm. The optimization objective, as we said, is mathematically the goal is to minimize the sum of these three residual computed over randomly sampled collocation points. This is a PD loss, the initial condition loss, and the boundary condition loss. So the advantage of pins include these parts. The appeal of this method lies in significant advantages which make it a powerful alternative to the traditional simulation method. It's a mesh-free, unlike the finite element method, which require complex spatial meshing. Pins operate on randomly sampled collocation points. This dramatically mitigates the curse of dimensionality problem associated with this kind of meshing in high dimensional problems. And also, this is a revolutionary feature, the data fusion. The loss function can incorporate both the PDE residual, this is theory part, and the sparse experimental measurements, the observation together. This allows PIN to seamlessly solve both forward problem and the inverse problem. And also the dimensional scalability, as we mentioned, this is a mesh free, so uh, it can scaling to better scaling better to high dimensional than traditional methods. And also it's hardware friendly. At its core, it's a neural network, so we can compute that on GPU hardware, modern GPU hardware for efficient parallel computation. So with these advantages, PIN have been successfully applied to many hard equations. For example, when solving the 2D Navier-Stokes equations, uh, PIN's predictions are very indistinguishable from the exact solutions. This success builds great confidence in this framework. So you can see that the 2D Navier-Stokes and this one, the KDV equations, we found that the PIN have achieved a great success. So, but everything seems to be fine until we find this. Uh, so, a central mystery emerged when research turned to a very simple textbook level first order PDE, the 1D convection equation. This equation is defined as the partial u to partial t plus beta partial u to partial x equals 0, and the initial condition is very simple. The ux 0 equals the sine x, and it has a periodic boundary condition. This one has a very simple analytical solution is that the sine x minus beta t. So it describes a very simple sine wave propagating as a velocity beta. However, the PINN's prediction was drastically different from the exact solution. The PINN's predict solution, it can match the initial condition, the sine wave at the time 0, but as time progress, it's completely false to propagate the waveform in the time domain. Yeah, so the network converts to an, we think, over-smoothed incorrect solution, resulting a massive absolute error. We call this failure mode. So further investigation revealed that this was not an isolated incident. PINs exhibit similar catastrophic failures when faced with a range of common PDEs. This includes the reaction, wave, and the electron quotients. In all these cases, the PIN converts to a physically incorrect solution accompanied by extremely high absolute error. This instance came known collective as the Pin's failure modes. This phenomenon was first found on NeurIPS 2020, a paper on NeurIPS 2021. This poses a systematic problem. Why would a framework that can solve complex Navier-Stokes equations fail on very simple 1D problems? This is a mystery this research sought to unravel. So our key contributions to this problem has two parts. The first is through analyze of this PIN's failure modes, especially focused on the information propagation during the optimization. We uncovered two main causes of this is we found two main causes of this propagation failure. And as a result, we propose a new state space model based approach we call PINN to address this issue. This is a paper we write in and we published on the International Conference on Machine Learning this year. And the second part, we further analyze the PIN's failure modes, but from a perspective of the optimization process, especially on the training precision. We uncover the true cause of the failure modes are due to under optimization, but not the known local minima problem. And then we propose a surprisingly simple solution to this problem. We find that just training on double precision can address this issue. This is a paper we published on neural information processing system NeurIPS this year. And also, I will introduce some of our interesting future work. So let's start with the first part. We will investigating from a modeling perspective. So, the red herring is PIN's failure optimization problem. Traditionally, for 5 years, the consensus in academic community was no, this is not an optimization problem. The reason is stem from observing the training graphs in failure modes, the loss does indeed drop significantly by several orders of magnitudes. We can see that in this one, it's from 1 times 10 power 6 level to a very low level. This means the training process, the optimization process is a success. Uh, yeah, because of by several orders of magnitude and converge optimization, we think the optimization is success. However, the error, you can see the orange curve, the L2 norm against the true solution barely drops at all. So it remains at a very high level. This low loss, high error phenomenon was universally interpreted to mean the optimizer did find a minimum in the loss function, but it was seen as a bad local minimum. The community concluded that the problem was not the optimizer itself, but the PINN's loss landscape was extremely complex, rocked, and filled with traps. So here is a classical perspective, the propagation failure. Based on this bad local minimum assumption, the classic viewpoint held that the root cause was propagation failure. The neural network was unable to properly propagate its information through the time domain. Yeah, so this part model like transformer, which attempt to use a transformer architecture to explicitly model this kind of temporal propagation. However, further testing showed that transformer still failed to solve the convection and wave equations. Although we can say that there is a performance gain with their model architecture, uh, yeah, they are still failed because absolute error is still in high level at the end of the time period. Yeah, mm, this indicates the problem remain unsolved and a deeper diagnosis was needed. So we want to find out the problem of the pins propagation failure. So our perspective is the continuous discrete mismatch causes this kind of propagation failure, and the simplicity bias of neural network itself uh, makes things even worse. So, from these two fundamental causes, we first introduce the continuous discrete mismatch. So, a neural network itself is a continuous function, is high-order differentiable across the entire spatial and temporal domain. But optimization is performed on a discrete set of collocation points. That's because of constraint of the computer, we can only do that kind of computation. So as shown in this theorem, we find that there can be infinitely many functions that satisfy the PDE only as those discrete points, but are completely wrong in between them. Yeah, so the neural network learns to cheat by minimizing the residual only where it's being checked and ignoring the continuity in between. This cumulative error eventually prevents the correct information propagation. And another thing we called simplicity bias. Simplicity bias of neural network is a well-known phenomenon in deep learning. That's when faced with multiple options, neural network tend to learn simpler, smoother, and low frequency function. For example, we have a classification task in the left. So both the classification boundary, this colored one and the green one, they are correct. The neural networks after fully optimization, it's always tend to choose this green straight line instead of a complex one. So for the convection equation, we can say that the U xt equals 0 will satisfy this governing equation and also the boundary condition, but but only the initial condition was not satisfied. So so there is a very large force that pushes the model to learn this kind of zero solution. Yeah, so the network find it's easier to converge in this simple mode than to learn complex mode, a high frequency propagation wave. The loss from the initial condition is not strong enough to fight the lazy preference for minimizing PDE residual. So our solution is we can try to use state space model. Yeah, based on this diagnosis, the failure is due to propagation failure caused by simplicity bias and discrete continuous mismatch. So we want architecture that it had to enforce consistency between points and also be forced to learn complex and high frequency dynamics. So this lead to a solution based on the state space model, the core of new sequential models like Mamba. Yeah, state space model are ideally for the problems as they naturally discrete continuous dynamics by describing the state transition of a dynamic system. Yeah, so we develop PINN Mamba. Yeah, the core idea is to employ a subsequential optimization strategy. We can in this work we trying to use a medium green sequence. This one the subsequence. We're modeling several collocation points together. Uh, in several, but not the whole time domains collocation points. Because in a long sequence, if we take the whole temporal domain, this will be very hard to optimize because of the gradient conflicts. Because of it will get a very large functional space to solve. And also, we not use a pseudo sequence introduced by Pinn's former. That's kind of simulating single time points are very easy to optimize, but subscribed into a very simplicity by to the simplicity bias. We use a subsequential modeling, simulating local spatial time point dynamics, strike like just right balance. It's easy to optimize and propagation information by aligning the repeated collocation points here. And we also eliminate the simplicity bias where this kind of subsequential contrastive loss. This is known. This is an this is something known in the machine learning community. So from this kind of subsequential and state space model based modeling, we can when we are trying to solve a point of the a collection points solution, we need to joint optimize the initial points and the points mm, itself and some points between the initial condition to the exactly collocation points. Yes, that means initial condition participates optimization of all collocation points. So the PINN members, this is a PINN members architecture. We can say that after getting some collocation points, we make a spatial temporal embedding of the collocation points. We send them to the PINN member encoder, just like this one. This is a traditional PINN member block with a state space model and with a 1D convolution to take this kind of subsequential collocation points. The only modification we made is we use a wavelet activation function. It's very simple. It's just alpha sine x plus beta cosine x. So after another transformation, we get the prediction. We call the subsequential prediction. Then after getting the whole sequence, we then align this kind of subsequential prediction with a contrastive loss. You can see that there are some overlapped collision points. We can only compute on this overlapped one. Yeah, so this is a PINN member framework. Using this kind of architecture, we solve the failure modes greatly. So you can see that PINN members results are exceptional in the convection and the wave problem. We can achieve a near zero level absolute error. This is a convection, and we compare with some baseline like vanilla PINN, the QRAS PINN former, and also CAM. Yeah, we found that PINN member can solve this kind of failure mode problem. And here is a reaction. Here are the results on the reaction problem. Yeah, you can see that the absolute error is also getting a near zero level. So for the 2D Navier-Stokes pressure prediction, the PINN members absolute error compared with traditional numerical method is even closer. Yeah, here is some results in the form of table. We consistently achieve state-of-the-art performance across different failure modes PDE benchmark.
Oh, hi. One question. By any chance, do you have the results with relative errors instead?
I'm sorry?
Do you have the results with relative errors?
Yeah. So this convection reaction with these three equations can be found on the original paper of PINN's failure modes that's published on NURBS 2021, and also all these results we include open source projects called PINN member. You can search on GitHub.
But I was asking if in your paper are you showing relative errors, like relative L2 errors? That is how usually people like compare the results.
Sorry.
With Chenhui, I think they're asking about did we report the absolute error or the relative error? Do we have the relative errors or not?
Yeah, I think this is a relative MA error.
Oh, so we're talking about 2%?
Uh-huh.
So we are talking about 2% error, right? For example, for the reaction case, and also for most of them, right?
Yeah.
Okay. And one question: did you compare with other methods, for example, like causality, because they also try to tackle all these things about what happened with time-dependent problems? Because did you compare anything with them?
Our focus is on the filler. So basically, we didn't try other PDEs. We only
No, not other PDEs. The same PDE,
yeah.
PDE with causality. Or this problem you can solve very easily. For example, if you can do resampling
Yeah.
of the points, or if you do adaptive local weights, you solve this problem, you nail it with much higher accuracy. So you compare with baselines which are not strong.
Yeah, because actually I was checking right now.
You can get very good accuracy for this problem.
Yes,
It's
I was checking
the paper. Sorry, Juan. The paper that you mentioned, we had the speaker here long time ago, but they were learning pins at that time. They had no idea what they're doing. They didn't use weights. They didn't use, So then they present as a whole paper. It's not a big deal. This is really trivial. For this problem, you can get accuracy 10 to the minus 6 easily.
Yeah, so I think their problem so we can combine their method into our method. We can even achieve higher precision, and higher precision and lower error on that kind of problem. We have an application study of the histology of our method to their method.
Yeah, actually, I was asking because I was just checking. Actually, there's this paper then you said that you tried cans, right? And for example, they tried this advection equation, and the constant is quite high, is 80. And I think that your constant is a little bit lower than that. And they get relative errors of 10 to the minus 5. And we're talking about a paper that it was also 2020. It was like an old paper. So, and what they were doing was just causality.
So maybe let's can this way, right? So wrong. We of course we didn't do all the comparisons for all the methods, right? This is whatever we presented here is what we have done the comparison, right? So we open source the code. So yes, if you feel free to check it out yourself too, or we can maybe afterwards, right? We can see if that's something we can add more comparisons. So I just want to maybe in interest of time, I'd like to just maybe to move on, just to see if we can finish the rest of the talk.
Yeah, I agree. Thank you for explanation. But I was just saying that, for example, claiming state of the art without comparing with all what is out there is a bit like a big statement. If you say you're state of the art, you have to compare with all the methods that are out there.
That's always difficult.
Yes,
right?
so this one we
always
are
difficult to make that claim. I agree with.
Oh no, but the causality paper has like 600 citations, right? So we're talking about like one of the main papers. We're not saying one that is hidden in the literature.
Yeah. Here we are trying to make a comparison of making an architecture level comparison. So we are comparing with other models, not other methods. We know that for some problems the NTK works. For some problems, the R3 resampling this can work. But we saw that they are not conflict with our models. So let's go to the second part. Professor Xiong, do you want to take over this part?
No, just go ahead. I think it's you already.
Okay,
yeah. Go ahead, please. Yeah, I'll
Okay,
jump if needed. Yeah.
Yeah, so we further analyze of the PINN's filler modes, but from the perspective of optimization process. if we look this kind of results, we will find that on different problems, although the loss itself are optimized to low level, we find that they are still different. Just as we are printed to declare victory, plot twist emerged. So we find that the field PIN on the convection problems, it has a loss of very larger than the PIN member. Although we think that's in a low level, this wasn't just a better solution. So it was a different order of magnitude for the loss value. This led to a hierarchical question: if PIN member could achieve a loss of one in -4 level, did this means the standard PIN with this kind of loss of 0.0239 was never fully optimized at all? So this directly challenged the 5 years community consensus that the low loss high error equals to a bad minimum. So there is a classical perspective saying that this is an extremely rough loss landscape. But after this kind of visualization, we can always find that there is a plane in the near optimization level. So the classical perspective of this kind of local minima problem is challenged. Yeah. So if we take a look at the dynamic of successfully trained models revealed a critical three-phase training process. So in the phase 1, the model is not converged. We can say that both the loss and the error, they are in a very high level. In the phase 2, this is traditional thought as a filler mode phase. So we can say that there is a high level of error, but with a very low level in regard to the loss. And after success, we find that there is a further inclining of the loss, both the loss and error. We call that a low loss, low error phase, a success case. This was a major discovery. The so-called PIN failure modes was not stable local minimum. It was simply transit phase that a successful model must pass through, but not get stuck in. So a failed PIN was one that maybe entered phase 2, but whose optimization process stopped permanently. Failing to enter phase 3 in this case, the success phase. So we propose 2 hypothesis testing. So the first is we call the loss barrier hypothesis. That means the failure modes and the success modes are into different loss basins. There is a energy barrier, we call energy barrier on the loss landscape that separates this kind of these 2 basins, so the optimization cannot cross this barrier. Another hypothesis is that the failure mode case and the success case, they are in the same loss basin, but the optimizer gets stuck for some reason. So we conduct a series of new experiments to confirm that this kind of same basin hypothesis holds. The evidence one is that pins itself always fail with random initialization. That means regardless of the random initialization, the pins optimization they fall into a universal basis, not a bad luck of the draw initialization. Since if we go into the if we go into the last basing, we can always find that there should be the case if we start initialization with this point. Yeah, and also the evidence too is that there is not really loss barrier from failure mode to optimized solution. So if we take a field model in phase 2 and reinitialize it to a continual training with a non-successful method, we can find that there is not a loss barrier. The loss would have to rise significantly first if this kind of hypothesis holds.
Excuse me, one figure shows error and the other one is loss, but what is the units for they should be different, right? But I don't see any other.
In this one, we normalize the both loss and error.
To what?
So to
the maximum. Okay.
Yeah.
But if you normalize it, shouldn't both of them be between 0 and 1?
Sorry.
Yeah, they normalize with one of them, like the maximum of one of them.
Yeah. So basically, this is normalized regarding to the original loss and error.
Then we cannot see any difference because for the blue line, we cannot see anything.
Yeah, because this is expected. If this kind of loss barrier hypothesis holds, it's expected that there is such kind of loss curve.
I don't think so. I think the scaling is not correct.
Yeah, but this is from our experiments. We continuously screen this kind of loss curve. We find that there is not significant there is not a significant increase in this process.
So now maybe we can, I don't know, what exactly you said is not the scaling is not right or something you said. And what Chenhui tried to explain, this is try to disapprove this hypothesis, right? If this hypothesis, if indeed it's this kind of a case, then you will see a jump in the error function. But I think maybe you're asking different questions, I think, right? Looks like. So you're asking, maybe the unit, maybe somehow it's not clear to you, right? And maybe, I don't know, Chenhui, can we explain how did we do the normalization? That's similar to the question, right?
Yes.
So how did we do the normalization of the loss function and the error function? I think Chenhui said with respect to the original kind of the solution, right? Which is not our initial point, but it's the baseline, the PINN number solution. Is that right?
Yeah, exactly.
One question maybe, did you try to confirm this hypothesis, like doing something like analyzing the loss landscape? Because this is a sketch of a loss landscape, right? I assume that if this could be true, you will be able to see actually.
That's our evidence tree. We make a visualization of this kind of loss landscape.
Oh, so this is a loss landscape? Like this is actual loss landscape, or is it like a sketch?
No, this is a sketch, and we have another we will show in the evidence tree.
Oh, okay.
Yeah. So here's the evidence tree. If we make a visualization of this kind of loss landscape, it showed only one basing. So if you take a look at the previous slides, you will find this row of one, but we will find there. We think that their visualization skill is not good because so it gets to a very high level, sometimes 10 powers 5 level. We don't. That means the visualization, the permutation on the is getting too large. That means the neural networks get too far away from the solution. So yeah, after examine the loss landscape, and also we find the error landscape. We find that there is a mismatch, right? So the loss landscape itself is much more flattened than the error landscape. That means if the optimization stops too early in some area of the flattened area, it might cause the error be significant than the loss declining.
And can I ask another question? The figure on the left is the same as the 3D figures on the
Yeah, they are the same.
But I don't know. The red one shows like 12.6, but on the right one you don't see that.
Yeah, so this is this show a larger part, I think. So this 3D one only showed this area.
Inside.
Yeah.
Okay.
Also, maybe I'm not. Could you please explain? So you're in when you go to the previous slide, you're essentially saying that in pings you should only have a single minima. You should sing a single basin, as you call it.
Yeah.
Okay. So there are not multiple minimas in pings.
No, we don't think so. We are trying to explain that the optimization part. So this part, the shown failure case, they are in the same basin with the success case. So after we don't claim that there is only one basin in the loss landscape, but we are trying to prove that every minimum of this kind of loss landscape, they are a success case, not the failure case.
Okay, so you're essentially saying that you will have a mainly like just one basin, but the rate as you're going to approach it will be really slow, and then you're going to be trapped outside of the true minimum. Okay.
Yeah,
okay.
exactly.
Thank you.
So this tree evidence shows that it has a higher probability that we should accept the same basin hypothesis instead of the loss barrier one. So if we accept this kind of hypothesis, but the question is why. But the question is why this kind of optimization stops. Yeah, because the failure and the success, they are in the same basin, but it's why it's always failure. Yeah, so there in the entire field of deep learning, the trend is always towards a lower numerical precision. Models that are quantized to int8, FP16, even sometimes 4 bits. This makes it even less likely for researchers to consider precision as a problem. But in scientific computing, this is not so. In some finite element method and other numerical method, people always use the double precision IP64 instead of a single one. But in the area of machine learning, because the default setting of on PyTorch on this kind of deep learning framework, they are single precision. People might just ignore this. Even worse, in the implementation of some version of the PyTorch, the FP32, the single precision is by default set to TF32. It's only 19 bits. It's only 19 bits precision instead of the single precision. So we find that inadequate numerical precision is the main reason why PINN stop optimizing in this failure case. We find that you can see that in the left with the FP62 training, the loss getting smaller, but the error optimization is stopped. But on FP64, after some points, you can see that there is a further declining in the loss, with a significant declining in the error. Yeah, so this means this means the precision itself getting very important in this kind of PINN optimization. We want to know why. So basically, we find that all these failure cases, they are using LBFGS optimizer. So the LBFGS is commonly used in PINN community, right? So but in the PINN, in the LBFGS itself has a inner loop and outer loop when it's implemented in machine learning framework like PyTorch. We find that the inner loops stop too quickly in the single precision training. Yeah, this is due to the order of magnitude difference between the gradients and also the updates each round. The gradients, so it's very easily rounded to zero because the gradient, also the updates, they are very easily to be rounded to zero because the gradient is too small. It's even it's even lesser than the minimum expressible numbers when at the scale of the weights. So we call this is a machine epsilon. So it's defined as the smallest positive number such that 1 plus epsilon. So it represents a relative precision of Floyd point number. So in FP32, it's
one question. So the conclusion that we're making here is that when you train a second order optimizer like LBFGS, you need double precision. Right?
Yeah.
Okay, got it.
So machine so in FP32, the machine epsilon is 1.19 if -7 is even larger than the tolerance change of LBFGS optimizer.
Sorry, one follow-up question from that. I think I've checked a few papers on things, but in general, when people use second order optimizers such as LBFGS, they defaulted to double precision, right? Because you need to consider all these things, not only about the gradient, you also need to consider like about the curvature estimations that they do, right? But in most papers they do, every time then they use LBFGS, they use float 62 or 64, right?
I don't think so. So, especially on the filler mode case, I checked all the open source projects. They are using IP32. They are using single precision, and also sometimes, by the choice of some PyTorch version, it's even smaller precision. It's getting to TF32.
Oh, okay. I see.
Yeah.
So I think this is something like of course, this is not a good practice, right? We discovered because of the neural network community, because somehow they kind of get used to this quantization and I mean, the people starting to probably abuse this quantization, to a certain level, right? And this is of course not a totally say we discovered this particular context. That is kind of we discovered, right? It's of course in general for the numerical optimization, yes. In the optimization community, people probably will not recommend using lower precision, for solving the optimization problem.
Yeah. Thank you.
Yeah.
Yeah. So, under FP64, the machine epsilon, it can be much smaller. It can get a much smaller number. So this means the gradients, also the updates, will not be easily rounded to 0. So we just use a vanilla PINN and try to use a FP64 training. You can see the result that results here. So the vanilla PINN with a double precision training can easily solve this kind of filler mode case. Yeah. That means we don't even need the architecture level things. We don't even need resampling. We don't need NTK. We don't need such kind of things. Just DNN with IP64 training, we can achieve a success on this filler mode problem. Yeah, here is the results in a table. Yeah, so basically we can say that the loss level is less than the all this kind of architecture based methods. We also tried NTK, but on the vanilla PINN, but this we have this similar conclusion that with double precision training, this kind of the vanilla PINN can even get a lesser precision, lesser loss, and also error.
But I assume that maybe here would make sense to give a little more context that when you use directly LBFGS, right? Because for example, if I see your Allen can, you get 1% with float 64. And I think that for most cases if you use just Atom and you train it for long enough, you can get to easily to 10 to the minus 3. We're using only Atom and only using Atom, so it doesn't make sense much to use float 32, right? Because it's first order optimizer, right? So maybe the right conclusion would be we need float 64 for second order optimizers, right? Or did you get any advantage also if you try to go directly only training with Atom?
Yeah, so we also tried Adam. We found that the first order optimization we don't think it can solve this kind of filler modes because first order optimization they are relatively cross grain, right?
Oh, I'm not so sure about that because, for example, for Allen can with single precision, you can get easily to relative errors of 10 to the minus 5. So it's like 3 orders of magnitude smaller than this one, right? With just for example for Allen can.
So for this kind of filler case, for this filler case problems, we don't find this phenomena. So our experiment shows that there is a consistently very large level when using of first order optimization.
I think that when you train it for long enough, I mean, because you have only three, in all your cases, you only have like 2,000 iterations. Most likely in that case, then first order will not work. But if you train it for long enough, or even around the same time, you will get to a good, relatively good performance. I'm saying just based on the
let him
magnitude.
finish because we are over time. Let him
Yes.
finish. We know the answer. We also use second order optimization, double precision. So no need to argue. Please go on.
So our we show that our method, not our method, this FP64 training is a standard method. They can apply to different model architectures. So it's a fundamental solution to the PINN. I think to the PINN community, and it's generalized about and it can be combined with other methods. For example, the NTK is other kind of optimization based methods. As this is the result, you can see IP6 consistently achieve a success error level. While the the single precision with some innovation on the architecture, it can only work on some of the architecture, but not all. So our future work is we are developing a higher precision GPU library. We are developing IP 128, even to 56. We are developing that kind of GPU library. So we want to support the entire scientific machine learning community with higher precision computing. This is our key takeaway. So from modeling perspective, the information propagation failure maybe the main cause of failure modes is from continuous discrete mismatch and some simplicity bias of network. We provide a state-based model based solution to that, and also from optimization perspective, we find that core problem with PINN failure modes is that the model is not well optimized. The failure and the success pattern are in the same loss basing based on our evidences, and insufficient numerical precision may lead to this kind of early stopping of optimization. So we find that using double precision or even higher precision is very important in the PINN as well as in the classic methods such as finite element method. So this is basically the key of our presentation today. Thank you for listening.
Thank you so much. So since we are over time, I think it's time to move on to our second talk. Mark, can you hear us?
Yeah, can you hear me?
Yes, exactly. And Chenhui, can you stop sharing your screen? Thank you so much.
Really interesting talk, by the way. Thank you.
Our second speaker is Mark Lower. He will be giving a talk on progressive sharpening is caused by layer-wise Jacobian alignment. Mark Lower is a staff research scientist at Clarify. After earning a PhD in mathematics from the University of Massachusetts Amherst, he worked at Booz Allen Hamilton and the National Geospatial Intelligence Agency on computer vision for object detection in overhead imagery. His research interests include computer vision, deep learning theory, and theoretical ecology. With that short introduction, the floor is yours and you can start your presentation.
Thank you very much. Before I get started, I just want to say I encourage interruptions and questions during the talk, but I cannot see the chat. because I'm in full screen mode. But if anyone has any questions, please feel free to just pipe up, because I'd like to make this as much of a conversation as possible. So yeah, I will be presenting today some work on the edge stability phenomenon and progressive sharpening done while I was in NGA with in collaboration with Catherine Kastner, who is also at NGA. So the structure of this talk is basically I'm going to spend the first half of the talk explaining some results from a previous paper by Jeremy Cohen that explains what the training on the edge stability and progressive sharpening is. And then in the second half of the talk, I'm going to explain how we extended those original results to actually explain where this phenomenon comes from. So, question?
Can you put it in presentation mode?
I thought I was. Let me see. Presentation mode. Do you know which I'm using Keynote. Do you know which
Does
You
anybody
try
know?
clicking the play button,
play
the play
slideshow?
slideshow. Yeah.
Yeah.
Okay.
Great. Now, yeah.
All right. Thank you. Okay, so motivation. I want to understand why neural networks work. This is sort of the $100 billion question for the AI community. We have these great algorithms that do all kinds of things that we couldn't do 10 years ago, but we don't really understand why they actually work. And when I say work, what I primarily mean is why do these neural networks generalize to new data? So we take the network, we train it on some data. We have reasonably good, not complete, but we have a reasonable understanding of why they're able to learn the data they're trained on. But what we don't know is why do they then work on data that they didn't see during training? Why do they generalize to new data? And we know from experiment that there do exist sets of neural network parameters that have very low train loss, but which generalize very badly. But we don't actually find these pathological parameters when we train neural networks in practice. You have to go looking for them. You can do things like take your test set, randomize the labels, and then add them to your training set. And the network will successfully memorize those random labels. But obviously that's not going to generalize because you've trained it specifically not to generalize. So these bad parameters do exist, but we just don't find them in practice. And that implies that there's nothing special about the actual neural network itself as a function. It's a combination of the neural network with the gradient descent-based training process that produces the parameters that go into the function. That's where the magic is. Whatever's going on here, it's got something to do with the combination of the neural network architecture with gradient descent-based optimization. And it turns out that that optimization does not work the way we thought it did. So the usual metaphor when I'm teaching neural networks is, we think of it as we're rolling downhill. We have this very high dimensional landscape where our horizontal position on the landscape corresponds to our current set of network parameters. And our height corresponds to our training loss. And we're sort of and we can't look at the landscape as a whole. We can only see the point where we're at, but we can tell the slope at that point, the gradient, and we can take a step downhill, downslope, and we sort of smoothly roll downhill until we reach the bottom of a valley, which is our minimum. But it turns out that's not actually what's going on. We're actually bouncing around all over the place. And this is what's called the edge stability phenomenon, which I mentioned as going to be basically the first half of my presentation. And I want to emphasize that when I say we're bouncing around, I am not talking about random effects due to stochastic gradient descent. Everything I'm going to present to you today is using full batch, non-random gradient descent. There's no randomness involved anywhere except for in our initialization. So what do I actually mean by that? So before I explain that, I do need to define some notation. So I'm going to use X to be the input to the neural network. So that could be an image, a time series, whatever. Y is the label I'm trying to predict. So that could be the image category or the value of the next time step. F is going to be the neural network I'm using to make the prediction. Theta is the network parameters. Little l will be a criterion measuring the difference between the network output and what I want it to be. And the training loss is then the expectation of little l over the training data set. So I want to make a clear distinction here between the criterion, which is a function of the network outputs, and the training loss, which is a function of the network parameters. And in particular, I'm going to assume that little l is convex, and the training loss famously is non-convex, but in practice, all of the criteria that I'm aware of are convex. So that's mean squared error, cross entropy, they're all convex. So when we do gradient descent, we are effectively solving this massive system of ordinary differential equations where the change in the parameters over time is equal to the negative gradient of that training loss. And since we cannot analytically solve that system of equations, we discretize it to, at every step, we calculate our current gradient, we multiply it by a learning rate, and we subtract that from our parameters. In practice, we use more complicated optimizers that include things like momentum and adaptive gradients. I'm going to leave that out of the presentation just for reasons of clarity, but I do want to note that everything I'm about to tell you does apply to more complicated optimizers with those features. So this does still hold if you use momentum and atom and so on. So we start with, so if we take the order 2 Taylor expansion of the to estimate the change in the training loss caused by one of these gradient descent steps, we get an equation that looks like this. So we have our original training loss, and then we subtract the linear component, which is just eta times the adjoint product of the gradient with itself, and then we have a quadratic product, which includes the Hessian matrix of the loss, and then we have some higher order cubic stuff that we're just going to ignore. And the thing that we're going to focus on is that quadratic term with the Hessian matrix. That's essentially the curvature. So when we take one of our gradient descent steps, our loss is reduced by some factor corresponding to the slope of the loss landscape underneath us, but then the slope is actually changing underneath us as we take our step. And if we step too far, we'll overshoot and our loss will actually go up, or at least not go down by as much as we expect it to. And that curvature is that quadratic term with the Hessian matrix. So to figure out how big of a step we can take, we define vi and lambda I to be the eigenvectors of that Hessian matrix. We know that our eigenvalues are real, and our eigenvectors can be assumed to be orthonormal because the Hessian matrix is symmetric. We then define ci to be coordinates of the gradient in terms of those vi. So since vi are orthonormal, we can use them as a basis. So my gradient is just equal to the sum of ci times vi. And then if we plug that into our order 2 Taylor expansion and do a little algebra, we get this. So now the change in our loss is equal to the negative learning rate times the sum of ci squared times 1 minus 1/2 eta lambda I plus those cubic terms. So as long as our cubic terms are small enough that we can ignore them, which in practice they are, the change in the loss will be negative, provided that 1 minus 1/2 eta lambda I is always positive. And that's what we want. We want our loss to go down. So we define lambda star, which we call the sharpness, to be the top eigenvalue, the maximum eigenvalue of our Hessian. As long as our learning rate is less than 2 over lambda star, our loss will go down, and we say the training is stable. If our learning rate is greater than 2 over lambda star, training is unstable, and we expect the loss to go up. So what Cohen et al. Showed was that in practice, the sharpness rises until eta is approximately equal to 2 over lambda star. And they showed that this happened for many network architectures, many data sets, many loss functions. It's one of those papers with something like 60 pages of supplemental material where they just go through more and more variations on the experiment. And the really weird thing is, so these are graphs taken from Cohen et al. Top row was using mean squared error as the criterion, bottom row was using cross entropy. Each curve is a different experiment. And what you can, and the middle and right curve graphs show the change in the sharpness over the course of training. And what you can see is that the sharpness consistently rises until it hits that dashed line, which is where the training is on the edge of stability. And if you reduce your learning rate once you hit the edge of stability, your sharpness starts rising again to compensate. So this hit me like a thunderbolt when I first saw it. It blew my mind because I took optimization when I was in grad school. And if you went back to 2012 Mark when he was taking optimization and told him that your sharpness rises until your learning is approximately equal to 2 over lambda star, I would have assumed that, well, your loss is just going to blow up then. Like, this is not going to work. Everything is going to, your loss will start increasing. Eventually, you'll start hitting nans probably really quickly, and it's just going to destabilize and blow up. But that's not what we see happen in practice. Instead, once you hit the edge of stability, your loss will go up on occasion, but it still goes down over time. So like your loss is no longer decreasing monotonically, but it's still decreasing on average over time. So this is really weird. And when I saw it, it just blew my mind. And I was like, I have to figure out what's going on here. And we think, this is not 100% nailed down, but we think, but in subsequent work, we think what's going on is that the sharpness is rising, but it's only only a couple of those eigenvalues are actually increasing in practice. So we see a separation of the eigenvalues of the Hessian matrix into a limited set of eigenvalues that are going up, which get called the top, and then the rest are just staying stable, which are called the bulk. And you are overshooting in the top directions. You're sort of bouncing back and forth over a really steep valley, but you're still making progress in the bulk directions, which is why your loss still goes down over time.
Hi, Mark.
So, yep.
I have a question here. So,
I was just about to say, and I'll now pause for questions before I continue.
Okay. So I'm curious if we keep reducing eta, I mean, like down to the machine precision, will the lambda star still increase? So I mean, is there a limit for that?
That is an excellent question, and that is actually one of the things we're going to do. I will say before I actually get into the details of that if you can make your learning rate so small that you never enter the edge of stability, because the sharpness keeps rising, but eventually training ends. You hit zero loss, and so as long as you make your learning rate small enough that you hit zero loss before the sharpness rises too high, you can avoid entering the edge of stability.
Okay.
You may also notice that in the cross entropy ones, the sharpness does go down at the end. This is caused by we'll get into the details later, but there's a known cause for that. It has to do with the structure of the Hessian of the cross entropy as a criterion. Once the cross entropy loss saturates, it starts losing operator norm. But we'll get into that in detail.
Okay, thank you.
Yeah. Other questions? I can't see anyone, so if people are confused, you have to ask because I can't tell from just looking at your faces. No questions?
I think you can continue.
Okay. So what we did was the first question I want to examine is what happens if you do have effectively an infinitesimal learning rate? Like, what if you actually solve the gradient descent dynamics exactly? And you can do this by just setting your learning rate to be really, really tiny, like you said, to machine precision, but that takes forever. So what we did instead was we borrowed a technique from stiff ordinary differential equations called an exponential Euler solver. which allows us to solve the gradient descent dynamics exactly without entering the edge of stability. I mean, or exactly up to machine precision. And I'm not going to go into details about how this works because it's a standard technique in stiff ODEs. I believe we are the first people to apply it to neural networks, but there is an extensive literature about this. It's very computationally expensive, which is probably why no one's used it before, but it does work. The second thing we did is I want to figure out where this sharpness is coming from. Why is this happening? So we decomposed the sharpness into components and measured each one individually. And basically the rest of this talk is going to be me decomposing the sharpness, measuring each piece, saying, well, it's coming from this piece, then decomposing that piece and figuring and tracing down through the chain where exactly this increase in sharpness is coming from. So we did this with we wanted to make sure that whatever results we got were going to be generalizable. So we did this on a lot of different data sets. I'm going to be mostly presenting results using CIFAR-10. So that's just a standard image classification data set trained with cross entropy. We varied the data set size, and for each combination of dataset criterion and dataset size, we ran 16 experiments with 4 different random seeds for picking the data subset and 4 different random seeds for picking the network initialization. Besides CIFAR-10, we also used a network trained on CIFAR-10 using mean squared error between the network outputs and a one-hot encoded label. We also had a time series classification dataset and a natural language classification dataset. Besides the ones that are listed here, we also did a couple more that, including a time series forecasting. There were a few others. However, anytime I update these slides, it has to go through pre-publication review again, which takes a month. So that's why they're not reflected here. But I'm going to be presenting results from CIFAR-10, but except for places which I will point out when this happens, everything we saw generalized to all the different data sets. So we start with what's called the Gauss-Newton decomposition, which I didn't come up with. This goes back to I found it going back at least to the 90s, but I have not actually been able to trace down the original source of this decomposition. So the Hessian matrix can be rewritten as the sum of a matrix G and a matrix H, where G corresponds to the second order partial derivatives of the criterion, and H corresponds to the second order partial derivatives of the network itself. So I want to make sure that the notation here is clear. So we're taking the expectation over the network inputs in the training set. And so that's why we have that expectation symbol. But G and H are both functions of the network parameters. And if we calculate the sharpness of G and H and plot them, this is what we get. So the plot on the left is the sharpness of the Hessian, the plot in the middle is the sharpness of H, and the plot on the right is the sharpness of G. So each curve represents a different experiment. The color of the curves corresponds to the size of the data set that the network was trained on. And you can see that the Hessian and G look almost identical, those two curves. And it's actually hard to see the sharpness of H at all. In fact, when I first presented this to people, they thought I had a graphing error, which is why it now has the red arrow. So whatever's going on, it has nothing to do with H. It has to do with G. So pause for questions.
Can we see the definitions of G and H again? Thank you.
Yeah.
So what's the difference here?
So G is so if this comes from just doing out the calculus of taking the derivatives. G is has the second order partial derivatives of the criterion, while H has the second order partial derivatives of the network itself. So so if you take the derivative of the loss, that's the derivative of the criterion multiplied by the Jacobian of the network outputs in terms of the parameters, and then you take the derivative again using the product rule.
So criteria means the norm, right? That with respect to which you minimize.
Yeah, that would be a good way to put it yeah. It's just not, that's just not a term we use in the machine learning areas I work in.
Okay, thank you.
Other questions? All right. So the next step in our decomposition is, recall that I said we're going to assume that the criterion is convex. So we can rewrite G in matrix form as the product of the Jacobian by the Hessian of the criterion by the Jacobian. And since we assumed that our criterion is convex, its Hessian will be positive semi-definite, so it has a square root. And I'm going to call that square root R. And in practice, we can largely ignore R. In particular, if our criterion is the mean squared error, then R is just going to be the square root of 2 times the identity matrix. So if we substitute that into our definition of G, we can rewrite G as the expectation of K transpose K, where K is R times the Jacobian of our network outputs by our network parameters. So G becomes a second moment matrix. So, sorry. So, and like I said, in practice, if you want to, you can just sort of pretend R isn't there, and this is just the Jacobian times the Jacobian. So if the sharpness of G is increasing, that can occur for one of two reasons. When we multiply a vector by G, it's mapped by K into the space of network outputs, and then it's mapped by K transpose from there back to the original space of parameters. So if the sharpness of G is increasing, that can occur either because the individual magnitudes of those K products are increasing on average, or it can occur because they're becoming more aligned. So the sort of the two extreme examples of what I mean by aligned would be, you can imagine that if K was just completely uniform and independently and identically distributed, it doesn't, every particular sample of K has some set of singular vectors, but those singular vectors have no relationship to the singular vectors of any other sample of K. And in that case, everything is just getting mapped it's getting mapped in and then mapped out. And the only way and you're picking up a change when you take the expectation over the set of Ks, the change in the magnitude of the product compared to the original vector is just determined by the magnitudes of the individual Ks. And then on the contrasting side, you can imagine that if K was just completely constant, so every sample was the same, in that case, the change, the change in the top eigenvalue is just going to be determined by the singular values of those individual Ks. So if the sharpness is increasing, this can either be because the Ks their individual singular values are remaining about the same, but they're becoming closer to that constant case, or it can happen because their individual singular values are increasing. So to measure which one of these is occurring, I define a quantity called the overlap ratio, which I cannot possibly be the first person to talk about this, but I have not been able to find a name for this in the literature. So if you know of one, please let me know. And I define it to just be the ratio between the top eigenvalue of the expectation of M transpose M divided by the expectation of the top eigenvalue of M transpose M. So in that constant case, this rho M would be 1, whereas in the case of their uniform IID, this rho M would be almost 0. So, and then the sharpness of G is equal to the overlap ratio of K multiplied by the expected squared operator norm of K. So if the sharpness of G is increasing, this can either occur because rho K is increasing, they're becoming more aligned, or it can occur because the expected squared operator norm of K is increasing, the individual samples of K are becoming higher magnitude. And what we see is that the overlap ratio is not increasing, which really surprised me when I first saw it. I was sort of expecting it to go the other way around. This is one of those cases where the results are not completely uniform. So when we use cross entropy, as our criterion, we pretty much always see a pattern that looks like this. The overlap ratio drops by some amount during those first few iterations of training and then remains roughly constant. When we use mean squared error, the overlap ratio does sometimes increase slightly, but it never increases by very much. I think the maximum was 20%, if I remember right, which is significantly less than the increase we observe in the sharpness. So whatever's going on, it's being caused by this expectation of the squared operator norm of k term. The individual k's are becoming higher operator norm rather than becoming more aligned. So I'll pause there again for questions.
So the criterion doesn't play any role because you are right. You're not looking across criteria, so it's just the k that comes in, the gradient of.
So the criterion does play a role in R.
But you said you leave that out.
No, I am including R. I'm just saying you don't have to pay attention to it because it's going to turn out not to matter.
Right.
So if you want to, you can just assume everything is mean squared error, and in that case, R is just the identity times a number.
But which criteria have you considered? Just the least squares and the cross entropy, or have you considered Sobolev norms, for example?
So far, we've only done cross entropy and mean squared error because unfortunately, I lost access to the compute I was using to run this.
Because a Sobolev norm, I could tell that would be very different.
Yeah. I haven't tested it, so I can't say for sure it wouldn't be different, but I would be surprised just because this has been consistent under so many different variations. But I can't say for sure because, like I said, I haven't been able to test it because I no longer have access to the compute I used to run this.
Thank you.
So the matrix G is way too big to actually materialize in memory. It's number of parameters by number of parameters. So that's, for a typical neural network, you'll have millions of parameters, so you'll have trillions of entries in the G matrix. And the way we've been getting its eigenvalues is we use power iteration methods, which let us, because we can get the Hessian vector products without needing to actually materialize G just using the PyTorch autograd engine. But one of the nice things about this K transpose K formulation is that the non-zero eigenvalues of K transpose K are the same as the non-zero eigenvalues of KK transpose. And K is number of outputs by number of parameters. So whereas G is enormous, KK transpose is actually quite small. It'll be 10 by 10 in typical cases. And this we can actually materialize. Furthermore, because of the way K is defined, because it's defined as R times the Jacobian has a block structure corresponding to the parameters of the network, which means we can rewrite KK transpose as the sum of layer-wise components. So we have K1, K1 transpose, K2, K2 transpose, where each Ki is the piece of K corresponding to a particular layer in the network. So then once again, we calculate each one of these individually and plot them. And this is what we see. And this is consistent. We see that in each case, the earliest layers in the network, the ones closest to the network inputs, have the highest sharpness. And in particular, there seems to be almost a geometric effect here where the sharpness of each layer I is equal to the sharpness of layer I plus 1 multiplied by some constant. That's not exactly true, but it seems to be something roughly like that. And so, but in all cases, it's dominated, the sharpness of G and hence the sharpness of the Hessian is dominated by K1, K1 transpose corresponding to the first layer. So everything I've done so far doesn't require that we be working with any particular network architecture, but at this point I'm going to, just for notational simplicity, I'm going to assume we're working with a multi-layer perceptron. And if we just do the calculus to work out what those Jacobians are, we can rewrite the Jacobians of the network outputs in terms of the network parameters in terms of the Jacobians of the network pre-activations. So we can rewrite our K1 transpose into like so. So we write Ki transpose in terms of delta I transpose, where delta I is written in terms of the Jacobians of the network pre-activations and the network activations instead of the Jacobians of the network parameters. And the reason we want to do this is that this lets me write each of those delta i's in terms of the next layer's delta I. So by chain rule, the Jacobian of the network pre-activations of layer I is just equal to the Jacobian of the network pre-activations of layer I plus 1 multiplied by a layer-wise Jacobian. So then each of my delta i's is equal to delta I plus 1 multiplied by that layer-wise Jacobian multiplied by some scalar term that corresponds to the magnitudes of the network activations. And one of the interesting things here is that for most common activation functions, the derivative of the activation function is approximately 0 for at least half of its domain. This is literally exactly true for ReLU, and it is approximately true for most of the other activation functions used in practice, like tanh. So that implies that these layer-wise Jacobians will generally be ill-conditioned. So if we take the expectation of these delta i's operator norms, we get this, sorry, let me back up a step. So we know that the squared operator norms are in expectation of these delta i's are increasing. And that could happen for one of a couple of different reasons. It could be that our scalar term chi I is increasing. It could be that our layer-wise Jacobians operator norms are increasing. Or it could be, again, that these are somehow becoming more aligned with each other. And so to measure the degree of alignment, I introduced a new term. Again, I'm sure this is in the literature somewhere, I just haven't found it, which we call the alignment ratio, which is just measuring the difference between the expectation of the product and the product of the expectations. And so that lets me decompose the expectation of the squared operator norm of delta I into the expectation of the squared scalar term, the expectation of the squared operator norm of the next delta I, the expectation of the squared operator norm of the layer-wise Jacobian, the alignment ratio of these delta i's with the layer-wise Jacobian, and the alignment ratio of the scalar term with the rest of the term. And then I measure each one of those individually and plot them. So the alignment ratio of the scalar term with the rest of it doesn't change at all. The scalar term itself goes down in expectation. The squared operator norms of the layer-wise Jacobians do increase by about a factor of 4. But as you may be able to guess based on the scale of the graph here, that is not enough to explain the change in the sharpness. And then the product of the alignment ratios increases by up to a factor of about 20. So what's going on here is primarily due to the alignment between these layer-wise Jacobians. So what does that actually sort of mean in practice, getting away from all these graphs and formulae? So at the start of training, we have some freshly initialized multi-layer perceptron, and we have some gradient signal at the end of the network, and we back propagate it through the network. At each layer, part of the gradient signal falls upon the singular vectors of the layer-wise Jacobian. Part of it falls on singular vectors that are amplified, and part of it falls on singular vectors that are diminished. And so part of the gradient signal is boosted and part of the gradient signal drops away. But on average, these roughly cancel each other out. The amount of amplification is roughly proportional to the amount that falls onto the part that's amplified, which is intentional. That's how the Xiong initialization is supposed to work. So in practice, the signal strength, the gradients, the strength of the backpropagated gradient remains roughly constant at each layer. After training, if we instead this gets these singular vectors of the layer-wise Jacobians rotate, so that instead the signal strength is boosted. So now the signal strength at the end, I'm assuming, is kept constantly the same. When I backpropagate it, again, part of it falls upon the part that is amplified, part of it falls upon the part that's diminished. But the part that falls upon the part that's amplified, the part that the vectors it gets mapped to is no longer random. It's now getting mapped primarily to the vectors of the next layer that are amplified, which then get mapped to the vectors of the layer below that are amplified again, so that the magnitude of the gradient signal increases as we go through the network. We just don't actually observe this in practice because at the same time, the gradient signals at the end of the network are also reducing in amplitude because we're getting closer to our target and our loss is declining.
Mark, before we move forward, I have a quick question, please.
Yep.
You show that the Jacobian alignment scales with dataset size by a power law, right?
Yep.
But doesn't more alignment mean network becomes more sensitive to input perturbations? Like
It does, yes.
how does this relate to generalization? Like, is alignment helping or hurting actually?
We don't know, but I asked the same question and I don't have a solid answer yet. It seems like it should be connected because the power law has the same form as the power law for the test loss. And
Right.
that would be a really weird coincidence if it wasn't connected.
Right. The second question, like it's connected actually, that what happens to alignment when you train on noisy versus clean data sets? Like, as these two are connected to each other, do you have a comparison over that?
So I don't have a comparison over that in my own work. I have some guesses about what's going to happen based upon what other people have shown, but I have not actually had a chance to run that yet myself. Just going back to the first question first, though, I suspect there is some sort of relationship here, but I will say that one experiment I did do is I tried measuring whether the degree of alignment was causally connected to the test loss. And I got really excited because I thought it was. And then I tried regressing, eliminating the influence of the dataset size. And the correlation disappeared. So the dataset size is correlated to the alignment, and the dataset size is correlated to the test loss, but the two do not appear to be independently correlated. But it's still it still seems like there must be some sort of connection. And my suspicion is that what this has to do with is some measure of the complexity of the function that the network is expressing, but I can't really justify that yet. That's just a hypothesis. And then for the second question, I have not had a chance to run that experiment yet. It is on my to-do list. Based on results that other people have shown, I believe that sharpness in the training data will significantly increase. Sorry, that label noise will significantly increase the sharpness. Just based on the results that were from, I'm blanking on the paper name. I'm blanking on the paper name, but in NeurIPS 2024, there was a paper that looked at something similar. And they argued that most of this was due to basically outlier signals, but I haven't had a chance to measure that myself yet.
Right. Okay. Because yeah, I think it would be really interesting to see those things happening. Yeah.
Yeah, the problem is there's just a lot of interesting questions to answer here, and every time somebody asks me a different one.
Yeah. Okay, thank you. Please. Thank you.
Yeah. Well, that is actually, yeah, so that is actually the end of my results so far. So yeah, so floor is open to questions.
So I was waiting on one thing for the whole discussion while it was happening. So I was thinking that maybe you will show that up, but like your Euler method avoids the edge of stability entirely, right?
Yeah.
So did you find any difference in final test accuracy or training time compared to regular gradient descent?
Great question. So the test accuracy was about the same, maybe very slightly lower. I didn't have enough results to say with confidence whether there was a meaningful difference or not. I think there's sort of an argument that the edge of stability is acting as an additional source of regularization noise. So I think the test accuracy might be a little bit lower, but if it is, the difference is very small.
Right.
The wall clock time for the exponential Euler solver is much worse. Just because it has to solve for Hessian eigenvectors at every iteration. The number of steps is significantly better. Especially compared to if you were trying to, and the wall clock time is better compared to if you were trying to actually keep the learning rate low enough to avoid falling into the edge stability.
Right. Can we just call it then a theoretical curiosity? I don't know.
At the moment, it's a theoretical curiosity, but I do think that I think that you brought up the question of input perturbation.
Yeah.
And I haven't done the experiments to measure this, but I suspect this is connected to adversarial perturbations.
Yeah.
So I think that at the moment, this is a theoretical curiosity, but I think that there's a lot of directions to take this into more applied realms. I know I keep saying like that's a great question. I haven't tested it yet. The reason is because for the last year I've been trying to, so rewinding back to this slide, if you look closely, let me see if I can zoom in.
Yeah.
Thanks. You may notice that the sharpness actually drops in like the first 10 iterations really precipitously.
Right. Yeah.
That's what I've been working on over the last year. And that's pretty much done now. So now that my plan is to next move on to answering some of these questions about like you asked, what if you have label noise? And in particular, how does this peak sharpness relate to the actual properties of the data set itself?
Right. Thank you. Yeah.
Other questions?
Great. Do we have any other questions for the speaker?
I dare you.
Hey Mark, this is Raj. Since you did, so I had a question. So
sure.
Yeah. So does Jacobian alignment also depends on the initialization of neural network, right?
Yes, that is another thing I haven't had a chance to measure very well yet. Other people have found results showing that so they haven't measured Jacobian alignment specifically, but they measured sharpness under different initializations. And since the two are so closely related, and the sharpness does vary with initialization, I think we can be confident that the Jacobian alignment varies with initialization.
Then also it will depend on the activation function because you need to choose the initialization based on the activation function so that your variance remains unity, right?
I did check that. And it does depend on the final values do depend on the activation function, but the shape of the curves all remain constant. So you still see the same phenomena where you have this initial drop in like the first 10 iterations, and then everything slowly ramps up, is consistent across the different activation functions I tried. But the final values are different.
And also just one question, like in the first few slide you showed the Hessian. So how does the way we choose the method for computing the Hessian? So suppose we compute full Hessian and we compute rank 1 update like Woodbury update something. So do you think that the both will reveal the same Jacobian alignment or something else?
When you say compute the Hessian, do you mean like the methods we use to compute the Hessian eigenvalue eigenvectors, or what do you mean?
The full Hessian for the loss functions, right? So
Yeah.
that will be very high dimensional. So like in second order, like quasi-Newton optimizer, we use rank 1, right? Rank 1
Oh,
approach.
I see. Yeah.
So how does that differ? Because if we are looking into the another optimizer superview like second order or quasi-Newton, so how does it behave? Do you have any intuition or comment on that?
Yes. So what we see is that the Hessian, I briefly mentioned this, but I kind of skipped over it a bit. The Hessian ends up with a very highly lopsided structure. So you end up with the Hessian ends up with about k eigenvectors, where k is the number of network outputs whose eigenvalues are really enormous, and then which the literature calls the top eigenspace. And then the rest of the eigenvalues are much more controlled and don't show this explosively growing behavior, which ends up being called the bulk. So any kind of low rank approximation to the Hessian, I would expect to primarily capture the top eigenspace.
Okay, so those are referred in other paper like dominant space, right? That
Yeah.
in which training happens, right?
Well,
Okay.
no. So one of the interesting results here is that there's this result that gradient descent mostly happens in a small subspace was the name of the paper. It's like, I think 2018.
Yes.
That I now believe, I am pretty sure that what this shows is that although the bulk of the gradient magnitude lies in the top subspace, it's not really doing anything. It's just bouncing back and forth. What the component of the gradient that is actually improving the loss is in the bulk, even though it's a lower magnitude component.
Okay.
And we did actually show this by basically, like, we projected onto the top and the bulk. This isn't in the paper, it's just another experiment we ran. We projected onto the top and the bulk and measure the effects of just training with either one. And with the top, just if you only use the top, nothing happens. It just bounces back and forth forever. Whereas if you use the bulk, the loss does consistently decline.
And I will share one more thing, because when you add regularizer to the loss function, even concept of dominant space is gone. It doesn't. So you always train in the full space, not in the fused mode. So when you add the regularizer to the loss function, then behavior is completely different. So
really, I haven't tried that.
Try that, and that is something we observe for the low dimensional data set, but I still have to look into the big data set. But the regularizer affect a lot these kind of the dominant space training and the bulk space training the approach actually. So
yeah, I can believe it. I will definitely look. I will definitely add that to my list of things to try. It's yeah. One of the questions I have here, which is what I think is what your question is getting to, is it is really unclear to me if this increase in the sharpness is actually something that is necessary for the network to generalize well, or if it's just some sort of side effect. And if it is just a side effect, could we potentially eliminate it so we could end up with neural networks that don't have these adversarial vulnerabilities? And if we could do that, it would probably look like some kind of regularizer.
Yes. Yeah. But anyway, very intriguing talk. Yeah, thanks.
Thank you.
I have so some time ago we had not too long ago, we had somebody from KAIST, I forgot the name of the Korean researcher, who actually presented the edge of stability, what you presented. Raj, I don't know if you can find the name of
Charlie.
Charlie, what's his last name?
Charlie Collahan.
From KAIST, right?
KAIST, yeah, KAIST.
Yeah. So he presented the edge of stability, but basically he said that the learning problem comes down to, I think, what he characterized as some actually work from Stanford before him, river valleys or valley rivers.
Yes. That's that. I was copying the same metaphor. Yeah.
Okay. So you didn't go to the rivers yourself, right? You just stay at the mountain.
Well, what the exponential Euler solver does is it lets us go down to the bottom of the valley and then follow the river along the bottom of the valley.
Oh, I see. So the exponential solver does that for you.
Yeah.
I see. So you don't actually have to explicitly construct. Okay. Can you explain how that happens?
So
just because you put an operator, right, in the exponent, yeah.
Well, so what we do is, and like I said, this is a standard technique. We didn't come up with it. I think we're the first.
I know the exponential integrator. Yeah,
that's what it is. Yeah, we are literally we don't calculate the full set of Hessian eigenvectors because that would be ferociously expensive, but we have a strong heuristic for the size.
Oops. Can't hear you. Suddenly we cannot hear you. Okay.
See, I can hear you. Can you hear me?
Yeah, there was a little interruption. Now it's good.
Oh, sorry. Yeah. So we have a strong heuristic for the size of the top subspace, the number of dimensions of the valley, which is, let's call that dimension n. We calculate the n+1 top eigenvectors and eigenvalues. And then we use the top n eigenvectors to construct a quadratic approximation to the local loss landscape, and then solve the gradient descent dynamics on that quadratic approximation exactly. And we use the n+1th eigenvalue to pick a learning rate at which we can be confident things will still be stable in that approximation. So what this looks like in practice is that once you reach the valley, it heads down to the bottom of the valley, and then the motion that would carry you back up the valley sides is just damped out really strongly.
Let me see.
I think that I'm pretty confident that there's a better way to do this. This was just the first technique I stumbled across in my lit review. I'm not an ODEs guy, but I've been talking to one at UCSD, and he is pretty confident that there are more efficient ways to do this, which hopefully will be in the next iteration of this work.
All right. Great. Thank you very much.
Thank you so much. Do we have any other questions for the speaker? Last one. Okay, I don't think so. So it's time to close the session. Thank you everybody for joining us today, and thank you, Mark, for giving that interesting talk.
Thank you very much for giving me the opportunity.